Turn on my other device. And then turn that off. So participants there, share screen, start meeting. Stop video, disconnect audio. All right. Got that, got that. Okay, first of all, this is my favorite book on chaos theory. This book is simple enough that you don't need a background in it, yet at the same time goes into enough depth that I was able to appreciate it in grad school when, you know, in principle I could have handled something harder, but it has enough depth that I could see some very, very fundamental ideas in there. Yet it's also simple enough that a lay reader could read it. If you're looking for something to read while hanging around inside, this is actually an amazingly fun tour through the ideas of the math behind chaos theory. Fractals, Chaos, and Power Laws by Manfred Schroeder. Okay, let's close that. Let's close that. All right. So today we are going to talk about diffraction gratings. Now, we've been talking about diffraction by one slit, by two slits. We did a little bit on three slits and whatnot. A diffraction grating is a very, very large number of slits. And when you get a very, very large number of slits, you get a series of roughly evenly spaced bright spots. And the really nice thing is that these bright spots are very, very sharp. So you get very little light in between them. And the angle that the light goes at depends on the wavelength. So blue light is going to these angles. Other wavelengths are going to different angles. So here we see white light going through here. Now all of them, some of that light goes at an angle of 0. So the white light goes there. But then you look at the other wavelengths and you see that after the initial white spot, there's a whole lot of nothing. Then you get the white light spread out from blue to green to red. And the angle that each wavelength went at is different, even though it was white light coming in. So this is a way of taking a light source, breaking it up into the wavelengths that it's made out of. And then if you were to put, here we got a detector screen, well, if you were to put one little electronic detector here, one little pixel there, another little pixel there, another little pixel there, just a row of pixels all across it, each pixel would only receive a specific wavelength and a few wavelengths very close to it, but you'd get just a very tiny range of wavelengths on each pixel. You know, one of them, depending on how you set up, might only get light from 500 nanometers to 500.5 nanometers. And the next one would get light from 500.5 nanometers to 501 nanometers, and so forth. And this is useful. This is, to this day, the main way in which scientists determine the spectrum of light emitted by an object, unless you get far out into the microwave range or you get far into the X-ray range. But for anything from ultraviolet to far infrared, they are almost always determining the wavelength of a source by sending it through one of these gratings and then seeing what angle does the light come out at. And if the source has several wavelengths coming out of it, then they get a whole bunch of different spots, and each spot goes onto a different pixel in a detector, and they see how much signal was received on each pixel of the detector. So it's an important technology. It's worth talking about. A few other things to know about them. First, as you can see from here, this is how people discovered that elements emit line spectra. This is how they discovered that if you heat up whatever element and make it glow, it doesn't just emit some uniform smear of colors, but it emits at specific bright lines. There's some background here from other things, but these are the main line spectra of different elements. Another thing is that these diffraction gratings, because they're a bunch of evenly spaced grooves, they look like a CD. Okay, a CD is actually a cheap diffraction grating in some sense. And for those who don't know what CDs and DVDs are, those are the things that we recorded information on, sound and video, before we could download our music and video. We had to carry them around on these little discs of plastic with evenly spaced grooves on them. Any questions on these before we get into the math behind them? Anyone? Going once, going twice. Okay. So that's the idea. Now let's analyze them mathematically. So we've got a whole bunch of slits here, and they're all evenly spaced. So one of them's at y equals 0, one of them's at y equals d, one of them's at 2d, then 3d, 4d, etc. And if we were to look at the path difference between one slit and the next one, it would be the same as always. It would be d sine theta, because theta is the angle that all these paths are making going to some distant detector. So then if we do our usual right triangle, this angle's 90 minus theta, this angle's theta, the path difference is opposite to theta, d's the hypotenuse, so d sine theta. And we learned last time that if we have a whole bunch of slits, then the diffraction pattern, the electric field of the diffracted light, will be a sinc function that depends on the width of the slits, multiplied by e to the minus I times k times sine theta times the y coordinate of the slit. And y slit here is just an integer multiple of the slit spacing. So we're going to get e to the minus I kmd sine theta multiplied by the sinc, all of that added up. We can pull out the sinc. And e to the I m something is the same as e to the I something then raised to the m power. And we're going to say that phi is kd sine theta. So we've got e to the minus I m phi, summed from m equals 0 to n minus 1. And this is why I had you do that homework assignment, adding up a whole bunch of complex numbers. Because these complex numbers, I should switch things I didn't put in the notes, and now I want to illustrate them a little more. All of these complex numbers are just equivalent to points on the unit circle, right? Here's phi, this is e to the I phi, this would be e to the minus I phi, then this would be, that's phi, this would be 2 phi, so this would be e to the minus 2 I phi. So every time we raise it to another power, we're just rotating along on the unit circle. So we've got a sinc function times the sum of e to the minus I m phi, just the sum of a whole bunch of things like this, all right? So we're just adding up a whole bunch of these complex numbers. And in most cases, you can just look at it. Whatever phi is, in most cases, we're gonna go around the circle. Now, if phi is smaller than 2 pi over n, let's say that, that phi is smaller than that. This might go, sorry, phi is larger than 2 pi over m. 2 pi over n. Let's make it concrete. Let's say that n is, well, what did I do here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I've got here m equals 13. So let's say that n is 39 equals, this is the maximum value on this drawing, okay? So I sum up the first 13, I go around once. I sum up the next 13, I go around again. And I sum up the next 13, I go around one more time, okay? For most values of phi, if I add up all of these complex exponentials, I've just got a whole bunch of lines in the complex plane pointing in all directions, a whole bunch of lines pointing in all directions, some either to 0 or something very close to that. What's the one exception? What's the one case where these will most definitely not sum to 0? They'll sum to something that is way far away from 0. Well, if they were all the same thing, right? If we go back to here, if phi is 2 pi, e to the minus I m phi is just 1, all right? And adding up a whole bunch of ones, there's no way that will ever get you 0. Even in politician math, you can't get 0 if you add up a whole bunch of ones. And so if phi is 2 pi times an integer, then k d sine theta, or 2 pi over lambda times d sine theta, is 2 pi times an integer. So d sine theta is an integer. So we're going to get a whole bunch of peaks when d sine theta is 0 or 1 or 2 or minus 1 or minus 2. And if phi is not 2 pi times an integer, well then in most cases, we're either going to get 0 or something close to 0. The only exception would be if phi was very close to 2 pi times an integer, so that we were adding up a number that isn't quite 1, but it's almost 1. And even if you add up n of those, each time deviating just a little bit, you know, first you'd be adding, let me switch back. I didn't think to put this in the notes. There's a whole bunch of things you realize you should put in the notes only once you're actually talking to people. So the only time that this would happen, that this would not add to 0, is if we were adding this and this and this and this and this, and just a whole bunch of things that are all really close to each other, okay? That's the only way that this won't sum to either 0 or something very close to 0. And that is why we get these very sharp dots in the diffraction pattern of a grating. Let's show that in Mathematica. I posted a Mathematica file that does all of this for us, all right? It's got, we fix the value of d, we fix the value of lambda, and then we define a function that just adds all of those up. And I left out the sync function because it's not the important thing here. All right, let's say the number of slits is 100. We get these very narrow peaks. Let's decrease the number of slits from 100 to 50. You see how these peaks get a little bit wider? Let's zoom in on one of those peaks. Let's take this sum. This looks like 14 to 16. So let's go between 14 degrees and 16 degrees. Okay. You can see that, of course, it looks actually kind of like a sync function. It's not quite a sync function, but qualitatively it has a lot of features in common with it. If you had to just do a quick back of the envelope calculation, you could start by approximating it as a sinc function, and you wouldn't be doing too badly. All right, so let's see what happens here. Let's actually take it from 15 to 16 so that we can get a really clear view of where the zeros are. This is going from about 15.25 to 15.55. All right, now let's increase the number of slits. So 15.25 to 55, that's a width of about 0.3 degrees. We double the number of slits, and now we're going from maybe 15.35 to 15.55, roughly. This is 15.5. This would be 15.3, 15.35, 15.5, 15.55. So we've cut it from roughly 0.3 something to 0.2 something. Approximately, oh wait, I was looking at the wrong one. 3.5 to 5, 0.35 to 5. Yeah, we've cut it exactly in half to 0.15 degrees. And the same thing happens to all of the peaks. If I zoom back out, minus 30 to 30, I'm not seeing too many other peaks. Let's all right, let's look at the next peak there, which is somewhere between 30 and 35. All right, so now let's look between 31.5 and 32.5. All right, so we've got a peak here. And with 100 slits, the peak goes from, I would say, well, this is 32.05 to 32.2 something, 32.22. So I would say about 0.17. And if we halve the number of slits, then it's going from a little bit less than 32 to a little more than 32.3. So now it's about 0.3 something. So again, having the number of slits doubles the width. What I want you to take away is that this is why people use a very large number of slits. If they don't use a large number of slits, then you don't get this very convenient thing where knowing the angle that the light goes at tells you the wavelength, or at least tells you something tells you the pretty closely what the wavelength is. So let's zoom out and let's do like 10 slits. Okay, if we have 10 slits here, that's not a lot. I mean, you can definitely see spikes, but at the same time, we can notice that there are other things going on. You couldn't get a really clean measure of how much light there is at each wavelength, because you'd see a spike here. But then if you got a signal there, you'd have to ask, well, is that due to what's here? Or is that due to some other source of light? And in principle, you could do that calculation and sort it out, but it's a much harder calculation. It would require a lot more careful data analysis. And I know for a fact that people find all sorts of ways to screw up this kind of data analysis, because at some point I spent a lot of time reviewing papers on data analysis algorithms. Any questions? Anyone? Going once? Going twice?
Professor, when you're saying, can you repeat what you said with like the more slits it has? It's like the more accurate the wavelength can be like calculated?
The more slits you have, the narrower these peaks become and the smaller these backgrounds become, which means that if you've got a very large number of slits, you know that the only way you're getting a signal here is if there's light at a wavelength satisfying the condition d sine theta equals lambda, or d sine theta equals 2 lambda, or something like that. All right? You know that if you have a large number of slits, the light you're getting here must only be because of some other wavelength present, not 0.532 microns. Here, let's make this concrete. All right, so here we've got a situation. I'm going to zoom out. I'm going to make d lambda 1 nanometer, okay? And I've done 400 slits, so it's going to take a while for Mathematica to compute all of this. All right, and you can't even see that there are actually 2 wavelengths there. So let's make d lambda 6 nanometers, and to make it run faster, make the number of slits 200 nanometers. Sorry, 200 slits, my bad. All right. So when you look at this, why is that not working? Even now, it's not necessarily obvious. So let's go to a range from 14 to 16. This was just working yesterday. Oh, because I did 6 microns instead of 6 nanometers. That explains a whole lot. All right, so here we've got 2 light sources. One of them at 532 nanometers, or 0.532 microns, and the other one at 538 nanometers. And these peaks are broad enough, these peaks are narrow enough that I can say that whatever I'm getting here is just due to 532 nanometers. That this peak is contributing, yeah, there's a tiny little bit of light from this wavelength that went to that angle, but it's minuscule. So I could say that anything I'm getting here must be the 532 nanometer light. And I can say that anything I'm getting here must be the 538 nanometer light, right? I can say that with great confidence. So this is a good system. Now, if I made the number of slits smaller, whoa. All right, now you see how the 2 peaks are not as distinct. I could still say that there's some 532 nanometer light here. I could still say there's some 538. But because there's a little bit of leakage, if somebody said to me, well, how much 532? I'd say, well, roughly this much, roughly that much. How much 538? Well, roughly that much. If I made the number of slits even smaller, would anybody care to even try to guess how much light there is at each wavelength? I certainly wouldn't. Let's make it something more marginal. All right, here, why? Here I can say, yeah, there's some 532, there's some 538. Exactly how much 532? I don't know. We're going to have to do some very detailed analysis. And we can do that math, but it would take a long time. But if we have a large number of slits, it takes a while for Mathematica to simulate it, but that's okay. Now I can say, how much 532? Well, it's got to be this much. It's got to be whatever that peak is, because there's, I don't know, maybe there's 0.01% of this light making its way to that angle. And maybe there's 0.01% of this light going to that angle. But for all intents and purposes, the signal I'm getting at this angle comes from one wavelength. The signal I'm getting at this angle comes from the other wavelength. Questions? All right, we could also, for what it's worth, do the exact calculation. The exact calculation would be we sum all of these, and there are actually formulas for summing simple polynomials like this. If we use one of those formulas for summing a simple polynomial like that, meaning that it's just 1 plus x squared plus x cubed, you know, that the coefficient of every term is the same, then it comes out to be this. And the intensity would be this times its complex conjugate. So we would follow that procedure. And we would multiply everything through. And we would get 1 minus cosine of n phi over 1 minus cosine of phi. And if cosine of n phi is 1, then, and cosine of phi is not 1, so as long as cosine phi is not 1, this denominator is non-zero. But if cosine of n phi is 1, the numerator is going to be 0. And so this is why whenever phi is 2 pi times an integer over m, you get zeros in the pattern. You get zeros in the little ripples there. You see all those little ripples there? Those little ripples come whenever n times phi is 2 pi times m. All right, here's some practicality. So if we set up something like this, y would be L tan theta. Theta would be the arcsine of m lambda over d, so y would be L times the tangent of all that. You're going to find that manufacturers rarely tell you D. Instead, what they tell you is the number of lines per millimeter. That's just the way that people do things in this field. So if we have 100 lines per millimeter, then D must be 1 millimeter over 100, or 10 to the minus 5, or 10 microns. Now here's where things get a little bit tricky. Let's say we've got a peak with m equals 1. Then sine theta, lambda over d, is 0.5 over 10 microns, assuming 500 nanometer light, or half micron wavelength. All right, so sine theta is 0.05. So theta is 2.9 if m equals 1. It's 5.7 if m equals 2. And if we send in 400 nanometer light, we get different angles. So far, so good. But now someone sends in some ultraviolet light with 250 nanometer wavelength, or 0.25 microns. So sine theta is m times 0.25 over 10. So it's m times 0.025. So we could have a case where sine theta is 0.05 if m equals 2. So it overlaps the 500 nanometer light, right? So when you get a signal at a given wavelength, somebody tells you, I got a signal at 27 degrees, and for the way I've got this set up, that corresponds to a wavelength of 580 nanometers. Well, that doesn't mean, that alone does not mean that they have 580 nanometer light. because it could be that they had a wavelength that is actually half of that. Because remember, what the grating is telling you is it's telling you the value of m lambda. If you know theta, and you know the lines per millimeter, well, from the lines per millimeter, you can get d. And from theta, you can get sine theta. So you've got d sine theta. Now, d sine theta might be lambda, might be 2 lambda, might be 3 lambda. You have to check. You have to do something else to figure out, is this source actually giving you 580 nanometer light so that m lambda is 1 times lambda is 580 nanometers? Or is it giving you 290 nanometer light so that m times lambda is still 580, but m is 2 and lambda is 290? Ways you could do that, you could look at other angles to see, well, if I've got the wavelength that I think I've got, I'm going to get peaks at this angle, but not that angle. You could know something about your source. You could put a filter in front of the source that blocks the shorter wavelength, but not the longer wavelength, and see if you still get the same signal. What I want you to take away is that simply knowing the values of d and sine theta does not tell you lambda. You need additional information to get lambda. Any questions? I have a friend who used to work at a company that makes diffraction gratings. And I know we're supposed to say that the customer is always right, but he told me a story of someone who said that they needed to tell 300 nanometer light from 600 nanometer light. And they wanted a diffraction grating that could do that. And my friend needed to be very, very careful to avoid saying that the customer is an idiot. So keep this in mind. Also, if lambda is larger than d, then there will be no peak, because sine theta has to be less than 1. So lambda over d had better be less than 1 in order for this to work. If lambda over d is larger than 1, then none of this will work. Now I want to show you something that isn't going to be emphasized on the test. I want to show you a more detailed analysis of resolution. This I'm not going to test you on because it's 10 minutes out of one lecture. The big ideas for this part of the semester are really about diffraction patterns. But it's worth making note of this. It's worth filing away in your mind. We'll deal with this in more depth in the advanced optics classes. But whenever somebody has an instrument, whenever your whole work depends on the accuracy of an instrument, you need to analyze its performance. And this goes to some of the ideas we were discussing before. Okay, d sine theta equals m lambda for a peak. And we established that the width of the peak is given by delta sine theta is lambda over nd. Yeah, that may not look familiar, but remember that what we've got is that kd sine theta, delta phi is the change in kd sine theta, and that's 2 pi over n going from the peak to there, all right? So here, kd sine theta is equal to, well, over here, kd sine theta is 2 pi m. And down here, kd sine theta is 2 pi m plus 2 pi over n. It's just shifted by 2 pi over n. All right? So delta kd sine theta is 2 pi over n. That's 2 pi over lambda d delta sine theta, because we're measuring theta here. Lambda isn't changing. We've sent in some fixed wavelength of light. And we're just measuring at different angles. Ooh, that should be 2 pi over n, my bad. So cancel, cancel. So delta sine theta is lambda over nd. Any questions on that concept? Anyone? These sorts of things show up a lot, by the way, in optics and wave analysis, that if you've got that the width of a line, the width of a feature in a diffraction pattern is inversely proportional to the size. Because if you think about it, last lecture I was saying, hey, the small features in a diffraction pattern have width have a width roughly proportional to the wavelength of light divided by the slit spacing. And then I said that the large features have a width that's inversely proportional to the slit width. Well, now if you think about it, ND, all right, so this little spacing would be D, the spacing between two slits. Spacing between top and bottom would be ND. And this is the smallest feature of all, or you could argue that this is the smallest feature, but they have the same width. The spacing between a peak and the first ripple, and between the first ripple and the second ripple, and the second ripple and the third, and so forth, that's inversely proportional to ND, which is the top, bottom spacing. All right, so this is just another example of what we were discussing before. All right, anyway, delta sine theta is lambda over nd. Now, we've got two wavelengths that are different but close. And I already showed you earlier in Mathematica that trying to tell apart two wavelengths that are close but still different could be hard depending on the width of the peak. All right, the width of the peak, the width of the line, people refer to these things interchangeably, had better be smaller than the spacing between the peaks, all right? So delta theta, well, we can get delta theta from delta sine theta because delta theta would be the derivative of sine theta with respect, the delta sine theta would be the derivative of sine theta with respect to theta multiplied by delta theta. So that's cosine theta, delta theta. All right? And we know that all of that is just delta sine theta, which is lambda over nd. So delta theta is lambda over nd cosine theta. All right, what's the spacing between the centers of the peaks? That's going to be theta at wavelength 2 minus theta at wavelength 1. That's going to be the derivative of theta with respect to lambda times delta lambda. Well, let's see. We're going to have to get the derivative of theta with respect to lambda. We could do some arc sines. I don't feel like taking the derivative of an arc sine. I don't have that memorized. I don't think many of you have it memorized because it's something that comes up only once in a great while. So I'm going to do a trick with the chain rule. I'm going to take the derivative of sine theta with respect to lambda, which is the derivative of sine theta with respect to theta. That's something I know. Multiplied by the derivative of theta with respect to lambda. That's what I'm trying to figure out. Derivative of sine theta is cosine theta. So I've got cosine theta, derivative of theta with respect to lambda is the derivative of all of this with respect to lambda because this is sine theta. M lambda over d is most definitely sine theta. And the derivative of all of this with respect to lambda, well, m is a constant, d is a constant. So I got some constants times lambda. When I take the derivative with respect to lambda, I've just got the constants. So cosine theta times the derivative of theta with respect to lambda equals m over d. So the derivative of theta with respect to lambda is m over d cosine theta. And delta lambda times the derivative of theta with respect to lambda is m delta lambda over d cosine theta. So this is how far apart these two peaks are. This is how much the angle changes when you change the wavelength of the input. You know, if we were to first shine light of one wavelength here, then shine light of the other wavelength, well, the grating would send one of those wavelengths here, producing a peak like this, one of the wavelengths there, producing a peak like that. The distance between them must be larger than lambda over nd cosine theta. So we can use a grating to resolve two lines or to tell two signals apart if this is all true. Difference between the angles is bigger than the width of the lines, or delta lambda is larger than lambda over mn. And this is why people will often use a diffraction grating not for the m equals 1 peak, but the m equals 2 or m equals 3. How high of an m they go to depends on certain practicalities of how they make the grating and everything. Any questions? Anyone? This is all perfectly clear. This is so clear that nobody has a question. I don't believe it. Somebody must have a question. This is one of those technologies that many of you are going to use. Much of physics comes down to analyzing the light that comes out of some matter so that we can learn something about the matter. All right, if there's no questions on that, nature produces its own diffraction gratings, and I want to spend a little bit of time on that. So nature produces diffraction gratings too. All right, it turns out that you can spontaneously get tiny spheres to form crystalline lattices. You can take tiny spheres of silicon dioxide, glass, or tiny spheres of polystyrene, stuff that's in styrofoam, or tiny spheres of PMMA, basically an acrylic. And these tiny spheres will just spontaneously line up, basically because if you've got them suspended in some liquid, all right, you've got a milky suspension with a whole bunch of tiny little spheres bouncing around. As the liquid evaporates, they get forced closer and closer to each other. And as they get forced closer and closer to each other, they, the droplet is shrinking. The droplet of water that they're suspended in is shrinking. So eventually, the only way to pack into space is to form these nice periodic arrays. This is why sometimes at a fruit market or in a grocery store, you will see the oranges stacked up in these hexagonal pyramids and lattices. That's why they stack them that way. And apparently this was there were conjectures that this was indeed the most efficient way to stack spheres. Way back in the time of Kepler, it actually became known as the Kepler problem. There's multiple Kepler problems. There's the Kepler problem in orbital mechanics in the solar system. This was a Kepler problem in geometry, but there was no fully rigorous mathematical proof until 1998. All right, so this is the most efficient way, which means that it happens spontaneously. And in grad school, I spent a lot of time doing that before I realized I'd be better off doing calculations. So I have a lot of pictures of this still lying around. And while we've just got a bunch of periodically arranged things that are often comparable to the wavelength of light, you can make these little spheres be 200, 300 nanometers, no problem. In fact, for silicon dioxide spheres, the chemistry is so simple, even I can do it. And I'm a physicist, not a chemist. Well, if instead of silicon dioxide, you use polystyrene, and then you put some material between the beads. If these are polystyrene, you put some ceramic material between them. And then you put them in a furnace so that the polystyrene burns. It's just plastic, but the ceramic stays. Ceramic doesn't burn. It's already oxidized. Then you can get periodic arrays like this. And people have done other things. People have found ways to stretch these systems. And what you wind up with is an artificial opal. This is an opal gemstone. It turns out that in nature, opal gemstones are just little beads of silicon dioxide arranged in periodic arrays. In some circumstances, silicon dioxide can spontaneously form in little periodic arrays. Sorry, silicon dioxide can spontaneously form spherical beads. It has to do with the pH. If the pH is strongly basic instead of acidic, then they will then silicon dioxide will condense as little spheres. All right, so you get these silicon dioxide spheres. They're in water at basic pH. Then the water at basic pH evaporates. The silicon dioxide spheres get packed together into periodic arrays. And so they wind up looking as colorful as a CD. You know, when you see those rainbow colors on a CD, that's a diffraction grating. Well, so is this. And that naturally occurs in nature. Block that. All right, the same stuff happens in beetles. And I have no idea why this is showing up here. All right, there are a whole lot of insects that have shiny exoskeletons. You look at certain kinds of beetles, their color changes when you look at them from different angles. And it's because they have little periodic arrangements of some kind of protein microstructure that forms little beads that gets periodically arranged in the shells. Why? I'm not sure. But back in the late 90s, early 2000s, this phenomenon of crystals of little spheres or beads with spacing comparable to the wavelength of light was a really hot topic in physics. So hot that a third of my dissertation is on it. And I never joined popular crowds, yet even I joined that popular crowd. So it was a really hot topic. And so people went around looking for beetles and other insects and any evidence they could find for the formation of these kinds of crystals in the natural world. And this is why beetles and other insects sometimes have different colors from different angles. As a matter of fact, you might talk to Dr. Vandervoort. He's working on making a freshman lab with that stuff in it to put in the physics for biology majors class. This sort of stuff could get published in the highest prestige journals, even though it was pretty easy work. And I just feel like it's important to mention that on the same page of that journal, there was a finding that chocolate is good for your health. I feel obligated to pass on this information from the scientific literature. I think it's something we could all benefit from. We could do other things with these. At some point, I took these beads and I arranged them in little channels. And so you could get arrays like this. The goal was to propagate light through these, basically use these as more complex versions of optical fibers. That wound up not happening for a variety of reasons, but that was the goal. You can do other things. People have found ways to take advantage of the natural propensity of microscopic spheres to spontaneously self-assemble into structures, and found ways to reproducibly make, say, little trimers or tetramers or pentamers. The 7-mer is interesting because you've got a ring of 5. You've got one sticking out in the front. There's another sticking out in the back. And so you get this 5-sided star formation, which turns out to be really hard to make in crystals. There are very special things about crystals with this 5-way symmetry. And so it was interesting that people were able to make that. Now, who says that the particles, these are called colloids, suspensions of little solid particles in water. Who says that the colloids need to be all the same size? people found that they could make all sorts of interesting symmetries if they used binary colloids. They could arrange things into different structures. Then they could play around with nanoparticles and arrange them into different structures like that and play around with the periodicity. So it's a way of making artificial crystals on much larger length scales. We're used to thinking of crystals as arrangements of atoms, but crystals made of atoms are hard to image. To look at something with atom scale resolution generally requires that you either scatter X-rays off of it and then try to infer the structure from the diffraction pattern like we talked about last time, or you use a very good transmission electron microscope, which is expensive and takes a lot of training to use. Optical microscopes, good optical microscopes aren't cheap, but they're cheaper and require less maintenance than a good transmission electron microscope. These are still electron microscope images, but they aren't atomic scale resolution. So it's at least easier than working on the truly atomic scale. There are actually people who study the packing of M&Ms. They study the random packing and self-assembly. And they say, okay, fine. And not that anybody cares too much about M&Ms, the science of M&Ms, but the packing of irregularly shaped disks and things like that is important in materials science. It's important in parts of biology. And if everything just depends on the shape and how things fit together, then why study molecules that you're going to have to look at with X-rays or electron microscopes when you could study M&Ms, which you can look at with eyes and cameras? So there's a little cottage industry of people studying things like that. These are, again, electron microscope images, but they're easier electron microscopes to work with than atomic scale resolution. And there are things called block copolymers, basically giant surfactants. A surfactant is a soap molecule. It's something that a soap molecule, one side of it is hydrophilic. It likes water. The other side of it is hydrophobic. It hates water. It likes fat. This is why soap is so good for cleaning your hands. It cleans oil off of your hands because there's one side of it that's attracted to fat. So it will attach to the oil molecules on your hand when you're dirty. And the other side of it is attracted to water, so it will pull them into the water. And this is, by the way, why soap is so good for getting rid of coronavirus, because coronavirus is surrounded by fat molecules. And so they're not soluble in water, but they are soluble in soap. Well, here these block copolymers are much larger. And so they could actually get the hydrophilic ends to stay around with each other and the hydrophobic ends to stay around with each other, and get them to form these banding structures. This is a natural way to spontaneously produce shapes just by combining the right types of polymers in the right ratios. So what I want you to take away is that you don't have, that diffraction gratings don't have to be made with, or things that diffract in periodic patterns don't have to be made by hand. Of course, in the lab, if you're going to use them to measure, you're going to probably make them by hand. But the natural world is actually full of molecules that will spontaneously form structures like that. Anyway, we are done with this. Next week is spring break, which you will get to spend in the most boring way possible, I'm sad to say. Don't worry, I never had a fun spring break in college. While other people went to the beach and had fun, I stayed in the dorm because I couldn't afford to travel anywhere. When we get back from spring break, we're going to spend 2 days talking about diffraction by circles and what it means for the resolution of a lens. And then we're going to start on the theory of relativity. So have as good of a break as you can, and remember to keep turning in your recitation activities if you're enrolled in that. And if you're not, but you want some extra practice, keep downloading them and working on them. Have a good day.